26.5 superconductors. The outline of this video is as follows. We will discuss the definition and historical discovery of superconductivity, followed by an exploration of critical temperature and how resistivity behaves in superconductors. Then I will introduce you to the main types of superconductors, metals and ceramics, and highlight their distinctive differences. We will examine the fascinating property of persistent currents, which makes superconductors truly remarkable. Next, we will look into practical applications, such as superconducting magnets and medical MRI technology. I will also explain the fundamental principles behind the BCS theory, developed specifically for metallic superconductors. Finally, we will cover the groundbreaking discoveries of high-temperature superconductors, and wrap up by considering the ongoing research efforts and the exciting potential these materials hold for the future. Superconductors are fascinating materials whose electrical resistance completely vanishes below a certain temperature, known as the critical temperature, or TC. Above this critical temperature, the material behaves like any ordinary metal, with resistance gradually decreasing as temperature drops. But as soon as the temperature hits TC, or goes lower, its resistance suddenly drops to zero, or at least becomes immeasurably small. A great example of this behavior is mercury. If you look at its resistance temperature graph, mercury behaves normally above about 4.15 Kelvin, and then at this temperature, resistance abruptly disappears. Just imagine running a current through a wire without losing any energy to heat. That is exactly what superconductors can do. It is truly remarkable physics, and understanding this phenomenon opens the door to all sorts of exciting technological possibilities. This slide presents figure 26.10, showing the relationship between resistance and temperature for mercury. As we cool mercury down toward lower temperatures, its resistance gradually decreases, following a typical pattern similar to other normal metals. However, once mercury reaches a specific temperature called the critical temperature, something remarkable happens. At exactly 4.15 Kelvin, mercury's resistance drops abruptly and completely to zero. At temperatures below this critical point, mercury becomes a superconductor, meaning electrical current can flow indefinitely without any energy loss due to resistance. This sudden transition to zero resistance is a distinctive characteristic of superconductors. Mercury was actually the first material discovered to exhibit superconductivity back in 1911. Understanding this phenomenon is vital because superconductors have numerous practical applications, from powerful electromagnets in medical imaging devices to potential future technologies in efficient power transmission. Superconductivity was first discovered in 1911 by Dutch physicist Heike Kamerlingh-Onnes, who noticed something truly remarkable while experimenting with mercury. As he cooled mercury below its critical temperature of 4.15 Kelvin, its electrical resistivity suddenly dropped to practically zero. Just how low is this resistivity? Measurements indicate it is less than 4 times 10 to the power of negative 25 ohm meters, which is about 100 quadrillion times smaller than the resistivity of copper at room temperature. That is an incredibly small number. So small, in fact, that for all practical applications, we simply treat this resistivity as exactly zero. Imagine electricity flowing through a wire with no resistance at all. No loss of energy, no heat generated, just seamless, perpetual current. This fascinating phenomenon opened doors to groundbreaking research and countless technological possibilities that we continue to explore even today. Thousands of superconducting materials are known today, and their critical temperatures vary significantly depending on the material. Interestingly, some recently discovered superconductors, especially ceramic compounds, have much higher critical temperatures than scientists initially thought possible. In fact, this exciting progress has opened new doors for practical applications, making superconductivity feasible at temperatures far easier to maintain. For example, Table 26.3 shows several materials and their critical temperatures, ranging from mercury at around 4.15 Kelvin to certain ceramic compounds, like mercury, barium, calcium, copper oxide, reaching as high as 134 Kelvin. That is quite a leap forward. These ceramic superconductors have attracted attention not just because of their increased efficiency, but also because they allow easier and more cost-effective cooling methods. With ongoing research, who knows how much higher we can push these critical temperatures? The possibilities are truly fascinating, and we are just scratching the surface of what superconductors can achieve. This table lists the critical temperatures for various superconductors, highlighting the wide range of conditions under which superconductivity occurs. Notice how these temperatures vary greatly from material to material. For instance, certain ceramic superconductors, like mercury, barium, calcium, copper oxide, have critical temperatures as high as 134 Kelvin, while traditional metallic superconductors, such as aluminum and zinc, have critical temperatures below 2 Kelvin. Among the ceramics shown here, yttrium, barium, copper oxide becomes superconducting at 92 Kelvin, significantly above the temperature of liquid nitrogen, making it practical for certain applications. At the other end, mercury, which was historically the first superconductor discovered, transitions at a relatively low 4.15 Kelvin. Clearly, the quest for higher critical temperatures has driven researchers to explore complex ceramic compounds. Because higher critical temperatures are particularly desirable, you can use simpler, cheaper cooling methods. Understanding these differences helps us appreciate the ongoing challenges and opportunities in superconductor research. Two main categories of superconductors are recognized metallic superconductors and high-temperature superconductors. Metallic superconductors are the classic ones first studied by Kamerlingh-Onnes, including elements like mercury, lead, and niobium. These materials typically exhibit superconductivity at relatively low critical temperatures. In contrast, high-temperature superconductors are more recent discoveries, often consisting of ceramic oxides, such as yttrium, barium, copper oxide. These superconductors have significantly higher critical temperatures, which makes them more practical for technological applications. Imagine the incredible possibilities if a room temperature superconductor were discovered. Why would this be so impactful? Because superconductors allow electric currents to flow without resistance, enabling the efficient transmission and storage of electricity and the creation of powerful superconducting magnets without energy loss. A room temperature superconductor would revolutionize everything from transportation and power distribution to medical imaging and computing technology, fundamentally changing the way our society uses energy. The critical temperature, known as TC, is sensitive to several important factors, including chemical composition, applied pressure, and molecular structure. Interestingly, some metals that are excellent conductors at room temperature, such as copper, silver, and gold, do not become superconductors even at very low temperatures. What does this tell us? Well, it suggests that simply having high conductivity under normal conditions is not enough for a material to exhibit superconductivity. There is clearly more involved here than meets the eye, and scientists continue to explore exactly why certain materials become superconductors while others do not. Understanding these factors could lead us toward discovering or engineering superconductors that work at higher temperatures. Imagine the technological advances possible if we could achieve room temperature superconductivity. It is an exciting area of research with profound implications for the future. A truly remarkable property of superconductors is their ability to sustain electric currents indefinitely without any applied voltage. How is that possible? It comes down to resistance being exactly zero. According to Ohm's law, voltage equals current times resistance. If resistance is zero, even when there is a current flowing, the voltage required is zero. Imagine setting up a current in a superconducting loop. Once established, that current can persist for years, showing no measurable decay. It is almost like perpetual motion, something we never observe in regular conductors. This unique ability to maintain stable, continuous currents, is extremely important for practical applications. For example, superconducting magnets used in MRI machines or particle accelerators rely on this feature, providing powerful, stable magnetic fields without needing constant energy input. Such persistent currents offer exciting possibilities, fundamentally changing how we approach energy efficiency and technology. Superconductivity enables us to build extremely powerful electromagnets, known as superconducting magnets. These magnets can generate magnetic fields about 10 times stronger than those produced by the best conventional electromagnets made from normal conducting wires. How is this possible? Well, the secret lies in the zero resistance of superconductors. With zero resistance, large currents can flow through superconducting wires without losing energy as heat. Remember, the power loss in wires is given by the current squared times resistance, but since resistance here is zero, so is the power loss. Researchers are even exploring superconducting magnets for large-scale energy storage systems, which could revolutionize how we store and distribute energy. Plus, there is already a major application you may know: medical imaging. Superconducting magnets are used in magnetic resonance imaging, or MRI, machines, allowing doctors to safely and clearly visualize internal organs without harmful radiation. Superconducting magnets are essential components in magnetic resonance imaging, or MRI, machines commonly used in medicine. MRI relies on powerful and stable magnetic fields to produce highly detailed images of internal organs and tissues. Superconducting magnets are exceptionally effective at generating these strong magnetic fields efficiently, making MRI one of the best diagnostic tools available today. One of the great advantages MRI has over other imaging methods, such as traditional X-rays or CT scans, is that MRI does not expose patients to ionizing radiation. That means it is safer for repeated use, especially beneficial for monitoring chronic conditions or guiding surgical procedures. By harnessing superconductivity, MRI technology continues to provide doctors with clearer insight into human anatomy and medical conditions, improving patient care while minimizing potential health risks. In 1957, a highly successful microscopic theory emerged to explain superconductivity in conventional metals. This theory, known as BCS theory, is named after its creators John Bardeen, Leon N. Cooper, and J. Robert Schrieffer. At its heart, BCS theory describes how electrons in metals can pair up to form what we call Cooper pairs. These electron pairs behave quite differently from individual electrons. Below a critical temperature known as Tc, Cooper pairs move through the material without experiencing any electrical resistance, resulting in superconductivity. For their groundbreaking work and the development of BCS theory, Bardeen, Cooper, and Schrieffer received the Nobel Prize in Physics in 1972. It is important to note, however, that BCS theory primarily applies to conventional metallic superconductors. To explain high-temperature superconductivity, scientists have found that modifications or entirely different theoretical approaches are often necessary. A major breakthrough in our understanding of superconductivity occurred in 1986, when researchers J. Georg Bednorz and K. Alex Mueller at IBM's Zurich Research Laboratory discovered high-temperature superconductivity in copper oxide-based ceramics. They observed clear evidence of superconductivity at temperatures close to 30 Kelvin in an oxide material containing barium, lanthanum, and copper. This discovery challenged prior assumptions about the highest possible critical temperature for superconductors, creating immense excitement and revitalizing research efforts worldwide. Due to the groundbreaking nature of their findings and the profound impact on physics, Bednorz and Mueller were awarded the Nobel Prize in Physics just 1 year later, in 1987. This achievement opened an entirely new field of exploration, motivating scientists to search for superconductors capable of operating at even higher temperatures. with hopes of revolutionizing technology and energy transmission in the future. Following the initial discovery, rapid progress was made in the field of high-temperature superconductors. In 1987, research teams in Japan and the United States achieved superconductivity at temperatures as high as 105 Kelvin using oxides containing bismuth, strontium, calcium, and copper, commonly known as BSCCO. Soon afterward, scientists discovered materials containing mercury, such as mercury barium calcium copper oxide, exhibiting even higher critical temperatures, reaching up to 134 Kelvin under normal atmospheric pressure and higher still under increased pressure. These developments are especially significant because the temperatures involved exceed the boiling point of liquid nitrogen, which is 77 Kelvin. Why does this matter? Cooling superconductors with liquid nitrogen is both cheaper and more practical compared to using liquid helium, which boils at 4.2 Kelvin. So these breakthroughs open the door for more widespread and affordable applications of superconductivity. Research into superconductors continues actively today, with scientists around the world exploring exciting new possibilities. One major goal is finding materials that become superconducting at even higher critical temperatures, perhaps eventually reaching room temperature. Imagine how revolutionary it would be to use superconductors without needing extreme cooling. Another key aim is understanding the fundamental physics behind high-temperature superconductivity, which remains partly mysterious to physicists even now. Finally, researchers are also working to develop superconductors that are easier to produce and shape, helping turn laboratory discoveries into practical technologies. As critical temperatures rise, it becomes more and more feasible to use superconductors in everyday applications. The outcomes of this ongoing research have enormous potential, from ultra-efficient power transmission to powerful magnets in medical imaging and transportation systems, transforming technology in ways we are just beginning to imagine. To summarize, superconductors show zero electrical resistance when cooled below a specific critical temperature, known as Tc. This fascinating phenomenon was first discovered in 1911 by Kamerlingh Onnes, who observed it in mercury at 4.15 Kelvin. A remarkable feature of superconductors is their ability to sustain persistent currents indefinitely, thanks to having absolutely no resistance. We recognize two main types of superconductors: conventional metals, explained effectively by the BCS theory, and high-temperature ceramic oxides, first discovered in 1986, which have significantly higher critical temperatures. Superconductors offer critical advantages in technology, particularly through their applications in creating powerful magnets, such as those used in MRI machines. High-temperature superconductors, with critical temperatures above 77 Kelvin, are especially valuable since cooling them becomes more practical and economical. Ongoing research continues to push the boundaries, exploring new materials and striving to achieve superconductivity at even higher critical temperatures, while deepening our understanding of this extraordinary phenomenon.